Okay, thank you very much, Juan, for the introduction, and thank you very much for the invitation. So the sound is perfect, okay? No problem? Yeah, good, perfect. Okay, so thanks a lot for the invitation. So today I'm going to discuss some results I got in collaboration with two younger colleagues, Bruno Premoselli from Brussels and Jean-Baptiste Casteras, who is now in Lisbon. So the problem we are looking at is the Lin-Ni-Takagi equation. And as you will see, I will discuss some specific results in a bowl about radial solution. So let me just start with a little bit of introduction about the Lin-Ni-Takagi equation. So one way to motivate the Lin-Ni-Takagi equation is to first talk about what is called the Potluck Keller-Segel system in Chemotaxis. So this is a system of two elliptic PDEs, well, parabolic PDEs, time depending here, parabolic PDEs. And you see that you have a special here coupling between the U and V solution. You have again U appearing here. And a specificity also of the problem is that since it's it comes from a system in biology, you have a Neumann boundary condition on the boundary. So in this system, you have that phi, this phi here. This phi is a smooth, strictly increasing function, and different choices of phi will lead to different results and well, families of results, but with specific equation when we will go to stationary solution. So let me mention a little bit the motivation of this system. In fact, this system comes from Chemotaxis. Well, chemotaxis is a movement of organisms, so I'm not going to detail too much on this, but just to say that in this system, this function U and this function V, they represent concentration of organism, and that means that at least at first, the interest is on positive solutions, since those functions have physical interpretation and are required to be positive, or at least non-negative. Okay, so in fact, a lot of attention has been given to this system, in particular to the dynamics. And to my knowledge, well, dynamics has been more studied when this phi of V is equal to V. And the first result is due to Nagai in dimension 1. He proved global existence in time. Then Nagai, Semba, and Yoshida in dimension 2. They prove that, in fact, you have global existence, with control on the initial mass, say mass, initial smallness assumption on the U0. So, of course, I associate to my PDE these two here initial conditions. And they prove that you have blowout in finite time if you are above this threshold. Okay. And then Herrero and Velasquez in dimension bigger than 3, they prove that you have blow-up in finite time. So there have been a lot of more studies, and in fact, even a very recent result, I think, by Juan Manuel, Jean Dolbeau, Monica Musso, and Zhencheng Wei. And then there are many other people associated to these problems, like Blanchet, Carrillo, and also Masmoudi, Winkler, Souple, and probably I missed some names. But there have been a lot of people working on the dynamics of this system. And of course, when you are studying the dynamic of a parabolic PDE, if you want to understand something about the asymptotic states or the asymptotic or the how the solution evolve in long time, you may ask, or it's interesting to study the stationary dynamics, so the steady states. And that's what's the purpose of my talk. And as many of you know, and especially there are experts on listening to this talk today, you know that when you have an evolution equation and you have some blowing up phenomena for the standing solution, you may expect that this blowing up phenomena also occur in when you look at the dynamics. So that's one of the motivation. I think when you look at the stationary say, I think that the people, those who observe that for the first time are Manuel and Juncheng Wei. Manuel and Juncheng observe that, in fact, when you have this system of two PDE, you have such relation here. So the divergence of this function is 0, and this implies that, in fact, this system of PDE is, in fact, only one PDE because you can relate U to V to this through this relation. U is a constant times the exponential of phi of V. Okay, so, and as I said at the beginning of the talk, indeed, when you take different choice of V, for instance, if phi of B is V, then you end up with an elliptic PDE with a right-hand side, which is an exponential term. Okay, and this is what people have been calling the Keller-Segel equation. On the other hand, if phi of V is a multiple of the logarithm of V, p minus 1 times log V, then you end up with a pure power nonlinearity here. And this has been called the Lin-Ni-Takagi equation because it has been first studied or introduced by Lin-Ni and Takagi. Okay, the constants epsilon here or epsilon tilde here, they are related somehow, and this lambda are related to the constants on the systems, but okay. And remember that at first people are interested in positive solution. Well, in fact, what I'm going to discuss can be also a little bit discussed at the level of any kind of solution, even sign-changing solution. But here we discuss positive solution. And remember also that we have a Neumann boundary condition. Okay. So let me say some few words about the state of the art concerning this equation. Well, there have been very much a lot of result on this equation. So it would be impossible to say all the results that exist on this. But let me mention some behaviors of solution when, in fact, just discuss a little bit what happened when this parameter epsilon here moves. Okay. People have been looking at this. Some people like to call it the singular limit or semi-classical state if you are thinking about the Schrödinger equation. Anyway, you let some parameter go to 0, and then you see that when this parameter goes to 0, it has the effect of, in fact, changing the size of your domain. So somehow your domain is expanding. If you let epsilon go to 0, your domain is expanding, and you are invading Rn in some sense. Well, not in some sense. You are really invading Rn if you rescale your function. Well, in the subcritical regime, well, when p is less than the critical Sobolev exponent, it has been shown that the solution at the limit when epsilon goes to 0, and here I'm talking about the pure power case, so the Lin-Ni-Takagi equation, the limit profile is a soliton. Okay, so it's a minimizer of the Gallardo-Nirenberg inequality, and you have that your function behaves like a rescaled center at some point, a rescaled soliton center at some point x epsilon, and this x epsilon is going to converge to a point on the boundary, but not. I mean, it cannot be any kind of point. It has to maximize the mean curvature on the boundary. Okay, and the equivalent result has been also obtained in by Kabeya and Ni in n=2. The case, this case here with a pure power is due to Lin-Ni and Takagi. Okay. Now, when p is the pure critical exponent, then in fact the concentration is much more delicate to observe. And again, you have concentration, and the profile is different because the profile is what we call the standard bubble, or the Talenti profile, or the Aubin-Talenti profile. So it's a solution of the Yamabe equation on Rn. And in fact, in that case, the existence of concentrating solution depends strongly on the dimension. So at this critical exponent, results are going to depend on the dimension. Okay, so what are the features of the result described so far? When we let this epsilon goes to 0, I have been discussing concentration, and it was always on a 0-dimensional set, so on points. And by the way, in the subcritical case, we had concentration on the boundary. In fact, very soon, people have been looking also at solution concentrating on higher dimensional sets. And if you want to prove existence or observe existence of solution concentrating on higher dimensional sets, it's always a good idea to look first at the radial case and to prove some concentration on points in a radial setting, which means concentration on spheres if you are in the original setting. And a first result has been proved by Malchior, Denis, and Wei. And it's let me show you in fact a picture. So this is it's not, in that case it's not very difficult to obtain those solutions by bifurcation analysis. By the way, this is not the point of view of Ni, Malchior, and Wei. They use the Lyapunov-Schmidt reduction method, but you can in fact prove that all positive solution. So recall that this I'm working with this equation here. So I'm working with this equation here, and I'm letting, I have P, which is an exponent, not necessarily subcritical, and I let epsilon go to 0. And in fact, it's not so difficult to show that you can build, or there exists a solution of this type. So having a prescribed number of zeros, and they all belong to bifurcating curves from some values epsilon I 1. So in fact, they bifurcate from the constant state u equal 1. Okay, because of course u equal 1 is always a solution of the equation. And in fact, this bifurcation diagram contains all possible positive solutions. And this has been proved. This can be proved by an argument due to Miyamoto. In fact, because you can parameterize your curves with the value at 0, and you can prove non-degeneracy. And if you fixed a power, then you are sure that all positive solutions are all positive radial solution are on one of these curves. And this solution, what do they have? They have these several bumps. You see, they can start with a value at 0, which is can be above 1 or below 1. And they have several maxima. And when you let epsilon goes to 0, you see that all these maxima, they are clustering to the boundary. Okay, and you have a concentration at 0 if your solution was had a value larger than 1 at 0. Okay. Now, in fact, there are more exotic results of that kind. I will not describe them in full details, but you can also build solution which will concentrate on higher dimensional set, and for instance on degenerate minimal submanifold. This is a result of Mahmoudi and Malchiori. And let me mention also for the Keller-Segel equation. So you have lambda epsilon v. In this case, one interesting parameter to play with is the parameter lambda. And Pistoia and Weira, they built with the Lyapunov-Schmidt method, they built a solution which blow up on the full boundary of the ball. So a radial solution that blow up on the full boundary of the ball. With, in fact, they were able to really describe the profile of the solution in a different region of the ball. So you have that inside, you have a kind of harmonic solution with a prescribed value on the boundary, and on the boundary you behave like a Liouville solution. Now this kind of solution were also built, and in fact together with Manuel Del Pino, again by Pistoia and Vaira, in a general bounded domain of R2, again with a full blow up on the boundary. And by the way, this had been constructed before by Malchiodi and Montenegro in a bounded domain of R2 for the Lin-Ni-Takagi equation. Well, there are other results, but I'm not going to describe them. But just to show you that in this business, many people have been working on concentrating solution. Again, in the Keller Segel, myself with Casteras and Norris, we have been constructing solution concentrating on internal layers. With Casteras and Roman, we have been playing again for the Keller Segel with a blow up at the origin and concentration on the boundary. And also for the Lin-Ni-Takagi, and this is closer to what I'm going to discuss today, we have been playing this time with the power P, and also in a paper with Grossi, Norris, and Terracini. And we had also solution which display concentration on internal layer. Now, what is my aim of today is a bit different. In fact, in the sense that I'm not going to play with the size of the domain omega. So I'm not going to play with a parameter in front of the Laplacian, and I'm not going to use another parameter lambda in, let's say, in the linear term or multiplying the nonlinear term. I'm in fact looking at the Lin-Ni-Takagi equation, and I will play with the power P. So the question of today is, what about stability result for this Lin-Ni-Takagi equation? So by stability, I mean that I will play with a power P that that will converge to the critical exponent. And the question is, can we have existence of bubbling solution? And if we can have bubbling, do we have bubbling? So can we construct such bubbling solution? Or do we have compactness? By which I mean that if I have a sequence of power P going to 2 star and a sequence of solution, then this sequence of weak solution has a limit and a good limit. I mean, it's pre-compact in some good norm. Okay, so let me say that this the motivation of this one of the motivation of this study, well, of course, recently many people have been looking at stability result for such kind of equation, playing with some parameter. Here we play with the power, but motivation comes from a bifurcation result that I proved some years ago, and that I would like to recall first. So the bifurcation analysis that I did with Grumio and Trossler 5 or 6 years ago is the following. So look at this Lin-Ni-Takagi equation and assume that you have a state which is a solution which is positive, could also be negative, but assume it's positive, and look at the linearization of the equation around that state. So if this linearization is has a kernel, so if there are non-zero solution of the linearized operator, then you may expect some bifurcation from this state U0. And of course, since you are working in a very nice setting, it's a radial, you have eigenvalues, simple eigenvalues, radial eigenvalues of your operator here, and you have a nice solution, which is a constant solution. You can say, okay, there will be bifurcation from this constant solution if this p minus 1 is an eigenvalue of minus Laplacian plus identity. Okay, and this leads to very simple results that I will comment, but let me first show a picture. So here it is, a picture. So each time you have an eigenvalue of minus Laplace plus identity, a radial eigenvalue, which is such that 2 plus this radial eigenvalue is smaller than the critical Sobolev exponent, then you have a bifurcation from 1 at that value, at that precise value. And then you can say, okay, can I follow the branch? And if I can follow the branch, what happens for those branch? Look at, for instance, here, if I have a bifurcation from a value which is above the critical exponent, you see that you have such phenomena which is a snaking phenomena that is reminiscent from those results about the Gelfand equation, for which Juan, by the way, is an expert. And so you can ask, what about those branches? What are they doing? And of course, when you see this bifurcation diagram here, it's for dimension 4 and radius quite large already. By large, I mean that you already have a lot of eigenvalues on the left of the critical exponent. You can ask, what about those branch coming from the left of 2 star? And they numerically, you see that it seems that there is a blowing up behavior when p goes to 2 star. Well, if you know quite well the elliptic theory, you know that if you have a sequence of solution with some value p which remains far away from this 2 star, then your branch cannot blow up because you will have any bound you like. So indeed, that's only place where your curve can go, but your curve could also go back to the right. So it can have many different behavior. But when you see that numerically, what you expect is that this is a conjecture. If you start from the left of 2 star and you look at the family of solution on your branch, then you expect that when p goes to 2 star, in fact, you have bubbling, or not, sorry, you have, you blow up, and you have bubbling, by which I mean that if you take the good rescaled profile, you converge to the right solution of the Yamabe equation in Rn. Okay, this on compact set, of course. Well, I'm not going to explain all the details, and those who know the famous Lin-Ni conjecture know that you have to be careful, at least in dimension 4, 5, 6, where things can be quite different. Okay, so I'm not sure I'm going to detail all the result, or the bifurcation result. The bifurcation result, somehow you saw it here in the picture. It's based on the Kandal-Rabinowitz theory. And since you are in the radial setting, you can show existence of continuum containing the bifurcation points. You can prove that close to the bifurcation points, you have C1 curves. You can prove that the solution remains positive along the branch. And in fact, you have two kinds of components on those branch. One that I will call BI minus, where the solution has a value less than 1 at 0, and BI plus, where the value has a bigger value than 1 at 0. And then you can count the number of zeros. This is classical. And yeah, something interesting. It's not very difficult to see. that if your solution starts with a value less than 1 along one branch, in fact, the solution remains uniformly bounded in the C1 norm. It means that somehow those lower part here, those lower branch here, they kind of exist for all P. Okay. Okay. Just to give you a flavor that this bifurcation can be very difficult to understand, because you see that in the case you have a bifurcation point on the right of the critical exponent, like here or like here, you see that in some cases, at least numerically, the branch go back to the left and seems to blow up on the critical exponent. But sometimes it doesn't. Sometimes it seems it does not go back, or sometimes it seems it blows up, but on the right of the critical exponent. So things are not very so simple. Okay. Well, maybe this I will skip. And so something about non-radial bifurcation, but this I'm not going to discuss this today. Okay, so let me recall the aim of my talk. So I want to discuss the competition between bubbling and compactness when P goes to 2 star. And so it means that I'm going to look at this family of solution of this Lin-Ni-Takagi equation. So at some moment, possibly sign changing, but even positive solution is already very interesting. And I have a sequence of exponents, and this sequence of exponent goes to 2 star. Okay, now just to go back to this bifurcation diagram, this is really the motivation, is to understand what happens to those branches. And I must say that without any assumption, it's very tricky to say something about those branches, because those solutions are built with a bifurcation theory, and so you don't have energy at hand. So you have no control. You cannot say that you start with a H1 bound or with a LP bound or whatever. So you don't know a single energy bound on those solutions. You only can extract a bound from the existence of the solution. So if your family is not, I mean, if you are not in a subcritical regime, as you know, you cannot expect bounds without assuming anything. And this is to say that to be able to classify solution, you will have to do some assumption. And the assumption that we are doing is the following. So we are assuming that U is bounded in some norm that we call L alpha K, and this alpha K, when pk is less than 2 star, this alpha K is 2 star. So I mean, in the subcritical case, so if we are approaching the critical exponent from the left, then we assume that, in fact, we have an L2 star bound, which is totally equivalent as asking that we have an H1 bound. This is totally equivalent, of course, from the Sobolev inequality. And on one side, and on the other side from the equation. On the other hand, if your exponent is higher than 2 star, then you see that we assume some bound on this pk over 2 minus 1 times n. And I would like to comment a little bit on this exponent. So as I said, if you don't assume anything, any bound, there is no hope to prove a result, at least in the supercritical case. In the subcritical case, you could say, okay, asking an H1 bound is something natural. In the supercritical case, observe that we ask something which is a little bit more than asking an LPK bound. So we are not just asking that this term here is integrable. So we are, I mean, when you multiply by UK, so we are asking more than an H1 bound. we are asking a little bit more. And let me comment on this exponent, and I think those who are acquainted with super critical equation know a little bit what I mean. If you have been constructing solution in that setting, the thing is that when you look at this equation, this Lin-Ni-Takagi equation, you have a natural scaling, at least for the operator minus Laplacian, and this pure power nonlinearity, which is the following. If you scale your solution like this, then you preserve somehow the equation. So at least forget about this linear term for the moment. You preserve the equation, and you will preserve a norm, and the norm you will preserve with this scaling is exactly the scale, the L alpha norm with this n over 2 p minus 2. So it's exactly the norm which is preserved. Now, another very interesting interpretation of, a natural way this exponent appears is that you all know that if you start with a pure power, pure critical power, so if you start with 2 star minus 2 here in the equation, you know that trying to improve this regularity with the W2P estimate won't work. You start with a L2 star bound, and in fact, if you do your classical, you try to start a classical bootstrap, at first iteration, what you get is only that your solution is again L2 star. So you don't win anything. And that's exactly the same that happens with this. If you assume that you have this integrability and you try to bootstrap it with the W2Q regularity, in fact, starting with this regularity in the equation, you will not improve it. You will get exactly the same integrability after one iteration. So that's somehow a natural, let's say, bound to a natural exponent to take, and it's, I mean, it's what we can do. That's something which is true, but also it has some, I mean, somehow it's expected that this kind of exponent plays a role. So our first result is the following. So it's a compactness result, and so it's in dimension bigger than 7. We have a super critical exponent, and then we prove, in fact, that in the supercritical case, there is no blow up when the dimension is bigger than 7. Okay, so we have pre-compact, we are pre-compact in C2. Okay, now in dimension 4 and 5, okay, so this, it means so no supercritical blow up in dimension bigger than 7. Now in the critical case, so this is a purely critical case. Remember that in the purely critical case, we are asking a H1 bound. We cannot have blow up except in dimension 3 and 6. So in the critical case, blow up can occur only in dimension 3 and 6. Okay, now this is the two pre-compactness result we have. So of course, you may ask, okay, assume you are not in those situations, you would like to somehow classify the possible blow up. If I cannot prove that my sequence is pre-compact, that's probably because I can have blow up. So the second step is to prove that if I have blow up, then necessarily I have some condition that appears. And then the third step will be, if I have those conditions, if I don't have pre-compactness, can I build those solution which blow up? This is going to be the third step. Okay, just to mention that when you want to classify configuration, blow up configuration, at least in well, in every dimension, but it's even more important in dimension 3. It's very important to have an expansion of your green function. And that's we have here. So this is the radial green function in our case. And this constant here in dimension 3 is what we call the mass. Okay, and this is going to appear in the next result I'm going to discuss. So as I said, if you don't have precompactness, you can say, assume you have blow up. We are in a radial setting, so it means that the L infinity norm is blowing up. And what it means that the value at 0 of the solution is blowing up. Okay. Well, what we were able to prove is that if we have a subcritical or critical blow up, then the weak limit, so the limiting profile, because in our assumption we have a H1 bound on the sequence, so we have a weak limit for this sequence of solution. Well, in dimension 3 to 5, the blow up, the limiting profile is 0. In dimension 6, the value at 0 has to be less than 1/2. And in dimension 3, the mass has to be negative, which means that we have to be on a ball of a radius bigger than R star. Okay. And what we can also prove is that between dimension 3 and 6, we can only have a single positive bubble at the origin. Okay. Now, if we have a critical, so this was a subcritical or critical blow up for positive solution. Now, if we have purely critical blow up, in dimension 3, the weak limit is 0 and the mass is 0. So it means that there is only one radius for which there is a specific radius on the ball at which you can have a blow up in dimension 3 in the critical case. And in dimension 6, you know exactly the limiting profile because u at 0 has to be 1/2. And if u at 0 is 1/2, it means that you know explicitly the solution because you are in radial setting. And again, you have a single positive bubble at the origin. Now, in the super critical case, we were not able to prove that you have a single blow up. We expect that you can build tower of bubbles. An amazing result would be to prove existence of infinitely many bubbles. I mean, you can prove the existence of tower of bubbles with the number of bubbles tending to infinity. But what we were able to prove is that in dimension 4 to 6, your limit profile has to be strictly positive. And in dimension 3, either it's positive or the mass, or it's 0 and the mass is positive. So it means again that the radius is less than a critical radius. Okay. So in the complement of all this, I mean, in all this situation, you can ask, can we prove existence of solution, of sequence of solution that display this behavior? And the answer is yes. So let me just recall, I guess many of you know, and I've been talking about bubbles, but let me just recall what is a bubble. So it's a function of this kind. So it's a Aubin-Talenti profile with a scaling parameter lambda k. And we say that the solution is the form u0 plus b if the solution looks like u0 plus b lambda k plus a little o of 1 when pk goes to 2 star. And as you see, those previous results show you that in some case, you will not be able to find bubbles as solution or bubbling solution with single bubble. You will really need to add a profile u0 because the weak limit of a bubbling sequence cannot be 0 in some cases. Okay, and this is the first result we have is in the subcritical case. So in dimension 3 to 5, we can construct bounded solution in L2 star of type B with pk going to 2 star. Okay, just a remark that we don't cover the case n equal 3, which is kind of special. This kind n equal 3 has been treated by Ray and Wei, not in a radial setting, but they are results in that direction. And in fact, our compactness result is still sharp in dimension 3 also. Okay, in the subcritical case and dimension bigger than 6, it is allowed to have a blowing up sequence of type U0 plus B. And this exists indeed. So if n bigger than 6, U0 is a positive non-degenerate radial solution with p equal 2 star. Then in the case n equals 6, we assume also that this is true. So the value at 0 is less than 1/2. Then we can prove that there exists a sequence of solution of type U0 plus B in the subcritical case. Okay, and we can count the number of zeros of those solutions. Just a word about what I mean by non-degenerate radial solution. Well, many of you know. So non-degenerate means that the linearization is trivial, so there is no kernel. And in fact, this is a generic property. I mean that if it's not true for, let's say, a given radius r on a ball of radius r, then it's going to be generically true for you perturb a little bit the radius of the ball, and it's going to be true. Okay. Now, in dimension 3 to 6, you can have bubbling in the supercritical case. Remember that in dimension bigger than 7, you cannot. And you cannot have solution of type B because the weak limit has to be strictly positive in dimension 4 to 6. And so it's natural to say, okay, let's try to prove existence of U0 plus B type solution. And in fact, this exists. And so the result is like this. Again, you take a U0, which is a non-degenerate radial solution at the critical exponent. In dimension 6, you need to assume something about the value at 0, and then you can prove the existence of a solution, of a sequence of solution of type U0 plus B in the supercritical regime. Okay, so this is exactly the classification I wanted to show you today. Now, just to finish, I will not discuss the details of the proof and so on, but just to give you a flavor of the techniques. So the constructive results are based on the so-called Lyapunov-Schmidt reduction. And to be totally honest, these are the main inspiration. So a paper by Micheletti, Pistoia, Vetois, and then a paper by Robert and Vetois. There are some also inspiration from a paper of Bakri and Casteras. The necessary and sufficient condition, they are based on a sharp, pointwise asymptotic description of the blowing up sequences. And in fact, since we have this, you see here, well, it's not exactly the equation I wanted to show, but if you, when you have a linear term here, there is a classical result or study by Solimini and De Villanova, which works without that term, but with the zero order linear term, things are a little bit more complicated. And in that case, we in fact took our inspiration from a paper by, well, I wouldn't say a paper, it's almost a book by Goussoup, Mazumdar, and Robert in the Memoir of AMS, and some paper by Premozelli, Vetois, and some preprints by Premozelli, Vetois. And in fact, the key point is a description of the possible blow up, the possible bubbling at the origin. And in fact, the key point is to show that if you have a blowing up sequence, it looks like the sum of alternating positive bubbles centered at the origin, okay? And they will concentrate at different rates, okay? So basically, you show that the blow up is of this type. You have that UK is equal to U0, which is your weak limit, and then a sum of bubbles up to some errors that you control depending on the rate of convergence of your parameter in the bubbles. Okay, so this is in the spirit of previous work which has been done, I think, by some authors that I already mentioned. Okay, so this is the precise construction, I mean description of the blowing up profile. And then the second argument, and I will just show you how to put these two things together. The second argument is the so-called Paralysis Identity that you write on a sphere at a radius delta k. I mean between delta k and big R, and you will play with this value delta k. You play with your Paralysis Identity. Then using the bubbling description I show, you have an expression for the L2 norm of the solution. You write your Paralysis Identity, and for instance, this is just to show you an example. If you are in the subcritical case with exponent with dimension 3 between 3 and 5, then combining this Paralysis and then this bubbling description, you have this kind of estimates which show you that indeed the weak limit is 0 in those dimensions. Another example is just to show you why we have pre-compactness in big dimension. In that case, again choosing the same delta k, which is the square root of the mu lambda k in your bubbling profile, then you can prove that the L2 norm of your solution along the sequence is bounding below by this value. You play a little bit with the Paralysis Identity, and then you show that you have this kind of inequality, and this show you a contradiction in dimension bigger than 7. Okay, I think I've been using all my time, so I thank you very much for your attention.